introduce a speaker. All right, welcome back everyone to another Quantum Matter seminar. It's my pleasure today to introduce Maria Gastiasoro, who's originally from the Basque Country, but right now she's working in La Sapienza in Rome, in the group of Jose Lorenzana. And today she's going to be working about superconductivity and ferroelectric modes. And please, Maria, the stage is yours.
Okie dokie. So can you see, first of all, thanks for this wonderful opportunity to present our recent work. So first of all, I just want to make sure, can you see my mouse? Yes, right? Okay, I'm gonna assume that that was a yes. As I said, I'd like to present our recent work, and the topic is pretty much self-contained in the title. So I'm going to be talking about how can you get superconductivity due to soft ferroelectric modes. And before starting, I'd like to acknowledge, where this work started, which was during my first postdoc at the University of Minnesota with Rafael and Andre, and also with Thais, which I think is the next speaker in your seminar. And then we did a review on this topic with Jonathan, and there is some ongoing collaborations that's been from those times in Minnesota. Then I moved to Rome, and the work I'm going to present today is basically what we've been doing over there with Jose, Eleonora, and Paolo. So this is the outline of my talk. The very first step would be to set the states. Superconductivity is an extremely wide topic, so I just want to make sure that I can place the topic of today in this context. I'll tell you a little bit. I'll introduce what polar metals are, and then I'll go into our work, which is essentially how to couple electrons and these ferroelectric fluctuations and get superconductivity. And then finally, once I have presented this model, which is this microscopic model, I'll show some results on, once you have the model, you get some estimations from, say, Ab-initio in a particular material, and I'll discuss whether this is a relevant mechanism for superconductivity or not. So before going into the details, I just want to zoom out a little bit and give you a bit of, so we know what I'm talking about. So as I said, you can get pairing from many fluctuations, bosonic fluctuations. So for instance, these hydrides are very, they are being extensively studied by, to some extent, most by this Ab-initio community. These are supposed to be the so-called conventional superconductors. So the pairing is mediated by lattice vibrations or phonons. Then you have the magnetic fluctuation mediated scenario. This could be probably relevant in cuprates, iron-bed superconductors, heavy fermions. This mechanism has been discussed, at least in this context. And the idea is you have some magnetic phase, and superconductivity arises, is sort of nearby or coexistent with it. And the idea would be, the fluctuations that come out of that magnetic phase could be the so-called, sometimes it's the glue for superconductivity. So today I want to discuss a third possibility, something that is somehow in between these two, where you get a superconducting dome in close proximity or even coexisting with a ferroelectric phase, and And then this could be relevant for systems such as strontium titanate, which has been the main motivation for our work. It's been studying extensively because it's been known for decades now that it's superconducting. And then it has had some kind of revival in the last few years. So the idea is, can ferroelectric fluctuations mediate superconductivity? And if yes, then what kind of superconductivity could we expect? So with that, I'll go into a bit of an intro of what polar metals are, because sometimes people think of ferroelectricity just in the context of an insulating material, and indeed, so this would be maybe relevant like a phase diagram for strontium titanate. So you have temperature, you have some parameter that you tune when you are in the insulating phase. This can be isotope substitution, it can be adding a little bit of calcium, it can be applying some pressure to your sample and so on. You can make it, or you can move the system closer to this ferroelectric phase. And then once you dope the system, you add carriers, and this system superconducts, it becomes superconducting. And because this superconducting phase can happen in this inside coexisting with this phase, I'll be talking about that kind of phase, a polar metal. So a little bit in speaking a bit more precisely, so you can think about this paraelectric to a ferroelectric transition as a transition where inversion symmetry is broken. And if this symmetry is broken when there is no carriers, this is a ferroelectric. If you have added carriers, there is still a polar axis that develops, but then there is no net polarization because the electrons will be screening all that out, and then you would have a polar metal. And often this kind of transition can be described by, or is accompanied by, the softening of a transverse optical mode. And here I'm showing the softening from hyper-Raman data of strontium titanate. So you see, as you follow the frequency of this transverse optical mode, the bare frequency gets extremely, soft, and eventually, even though it should cross the zero and go into the ferroelectric phase, it sort of gets this kind of curvature, which is been said that is because it's a quantum paraelectric, and this never goes into the order phase. It's a prototype of an incipient ferroelectric. Okay, and now if I want to visualize what this mode is, you can think that you have, for example, the titanium and the oxygen cage here moving relative to each other out of phase. This sort of creates like an electric dipole, if you want, and then across the transition, this mode would completely freeze out. Okay, so when I'll discuss today the coupling to the ferroelectric fluctuations, what I'll be doing is coupling the electrons to this kind of polar mode. And then why am I trying to see whether this mode or these ferroelectric fluctuations are important? So there has been, in the last few years, a lot of different groups, different experiments showing that there is an intimate connection between how close you are to this ferroelectric phase and what TC does with the superconducting phase. So, for example, there's been reports saying that if you move the system closer into the ferroelectric phase, you can get enhancements up to a factor of 3, and so on. So now the idea is, could this coupling between the electrons and the ferroelectric fluctuations be the main ingredient or the most important thing most important mechanism for superconductivity, because this is somehow a bit of an indirect indication that these fluctuations might be important. Something that I would like to point out before going on is the fact that these are extremely low carrier density systems, so their Fermi energies are around 5 MeVs, 10 MeVs, 15 MeVs, and so on, and that place them in an energy regime where the Fermi energy is much, much smaller than the bifrequencies, that your characteristic phonon frequencies, if you want, that usually one looks into to apply the conventional electron phonon kind of superconducting pairing formulation. So all the tools that we have are controlled in the limit where the Fermi energies, the large energy scale compared to the phonon degrees of freedom. So you have the picture of a fast electron and a slow lattice vibration, but this is not the case here. And this puts this is a challenging regime, because if you want to couple it to modes that are at much higher energies, you have to be a little bit careful with the formalism that you apply. So what I'm going to do today instead is couple these electrons, which have very low Fermi energies, with a mode that is very soft. And the fact that it's very, very soft puts it in a regime where, if my mode is about 1 MeV, even if I have a Fermi energy of 10 MeVs, it's still in the conventional adiabatic regime. And then in principle, all these BCS, Migdal-Eliasberg tools are in principle okay to be used. So this is something that I wanted to point out. This is one of the big challenges. And I'll say a little bit more about on that at the end of the talk. And then that being said, I would also like to point out that this is a problem that has been studied quite a bit. And lately, like I would say that the main two parallel mechanisms have been using either the dynamically screened Coulomb interaction that would be due to longitudinal modes. This is, for example, what you would have if you want to explain a system that is superconducting due to plasmons. But the one that I'm going to discuss today is the second one, is the one where you couple the electrons directly via some exchange coupling to the ferroelectric fluctuations. And then I think something also very interesting that has not been explored too much, that maybe goes even beyond this, what is the mechanism here, is that when you dope the system in, and you start from the ferroelectric phase, so you start adding carriers, then you're in a polar metal, so that means that your inversion is broken, you have a polar axis, and now it becomes superconducting. And I think it was last week, there was this archive paper on archive claiming that you may have topological superconductivity in this kind of situation. You have all the classic ingredients: spinor recoupling, inversion, symmetry breaking, and superconductivity. So I think this is also a very interesting thing to think about. And then to finish with the introduction of this arena of polar metals and superconductivity, there's been also recently another set of experiments based on sibling of strontium titanate, so that would be KTO. And in this case, instead of being bulk, what they do is they make these heterostructures, or they also can dope the crystal with liquid gating. And in any case, what they find is that the two-dimensional electron gas that is formed superconducts, and it has TCs that are much higher than measured in, for example, bulk STO. And there might, I'll explain a little bit in the end, that there might be indications that a prominent mechanism for pairing this system may be this direct coupling to the transverse optical mode. So with this, I'm done with the setting up the states, and I'll go into the issue of how do I couple the electrons and these ferroelectric mode, which is a transverse optical mode. So I'm showing it here, and with a little bit more details if you want some cartoon, where I'm showing the local displacement, if you want, this dipolar displacement of the phonon, which is propagating to the right. And that means that U and Q are perpendicular. So when you go to the linear coupling in a textbook of electron phonon, you find the ferroelectric coupling. This one is Q per C dot U. That means that if your displacement is perpendicular to the propagation, in principle, this varies exactly. Now, if you take into account the corrections from the fact that you don't have a complete isotropic system, these systems have a lattice, so that means that there's going to be some crystal corrections, and it's not fully transverse. This mode is going to have some longitudinal components, but it's been estimated that those kind of components will be extremely small. So this coupling is a little bit challenging to, using this coupling is maybe not the way, I'd say. Another very recent way to couple to this, ferroelectric soft mode is via quadratic coupling. So now the coupling would be, instead of to linear order, you go to next order. And there is very recent indications that this coupling might be very relevant in this system. I'm not going to discuss that today. Instead, what I'm going to do is I'm going to go back and stay in linear coupling. And what I like you to show today is how to get to linear coupling. So linear in U, a finite coupling, where now I'm connecting somehow this U to the spin of the electrons. And this is a non-magnetic displacement that is somehow talking to the spin. And how can that be? And that is because I have to allow for spin orbit. So it was pointed out a few years ago that if you allow for spin orbit coupling, you can get a Rashba-like, because this has kind of a Rashba-like coupling between the electrons and anything basically that breaks inversion. And then what I'll do next is show from a microscopic point of view how this kind of coupling arises in these systems. Before going into the coupling, I have to say a few words about the electrons, right? I told you what the phonon is. Now I have to give you a brief description of the electronic part. So in strontium titanate, you have the conduction band around the zone center. It can be mostly described by the three T2G orbitals, the XC, the YC, the XY, and then you have to add spin orbit coupling, because at the Fermi energies that you're at are comparable to the spin orbit coupling energy split. So here I'm showing explicitly this. You would have the three T2G orbitals would be degenerate. As soon as you switch on spin orbit, what happens is that six-fold degeneracy is split into a doublet and a multiplet down here. And then you're gonna start filling up those bands, and these Fermi energies are gonna be of the order of this spin orbit coupling gap. So because I'm gonna be using these bands to show how the coupling to the transverse optical phonon mode works, I'll be using this kind of picture. So I just want to show you, like, this is nothing but, so spin orbit coupling, you are adding an effective L equals 1 from T2G orbitals, L equals 1 orbital degree freedom with spin 1/2. So for example, this one here, which is the 3/2 plus minus 3/2, is mixing just two of the orbitals. So I'll focus on that particular states, because instead of having three orbitals, you're only mixing two, and then it's a little bit more simple to show. And then in that particular case, for example, how do you get the new pseudo spin, which is going to be plus? You are adding, with plus I, the spin up of the X and Y orbital. How do you get the pseudospin down, the -3/2. It could be doing the same, but with -I and the spin pointing down. So basically, this spin orbit coupling is locking the spin. Is no longer completely free in this SU2 world. Is locking it to the orbital and to the angular momentum, parallel to the angular momentum. And now, thankfully, in strontium titanate, there is a further reduction of the symmetry where the system goes from cubic to tetragonal. And here, basically, you can see maybe more clearly that as you fill up these bands, you go from bands 1, 2, and 3. The Fermi energy will go up to, I don't know, in these energy scales up to around 50 MeVs, and the spin orbit coupling gap is around 30 MeVs. So the basis to be thinking about in the conduction electrons might be more appropriate. The more appropriate basis is probably the spin orbit coupling, or this total J bands. I'll be focusing, as I said, on this one here, because also luckily the lowest band, which is this n=1, is essentially the one that mixes these two orbitals. So now, how do I couple this lowest band to a transverse optical phonon? I'll show you first how the mechanism works, sort of with these pictures, and then I'll show the same thing with in mathematical form. So the first, it has basically 2 or 3 steps. The first step is once I shift the oxygen cage with respect to the titanium, which is shown here with this, the oxygens have this p orbital. So once I shift this to a finite polar displacement, there is a new channel that is allowed, a new hopping channel between the different orbitals. So if this displacement, if u is equal to 0, if there is no polar displacement, then you can't have by symmetry a hopping between these y and x t to g orbitals. So this interorbital channel would be forbidden. Once you break this mirror symmetry here, this is, is odd, even nowadays that is no longer the case, and you can have a hopping. Because this optical mode breaks inversion, the hopping that happens to the right and to the left will also break that inversion. So now the channel, hopping to the right would be with plus t, and hopping to the left would be with minus t. You can even follow that with the colors. You have blue, 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 that's positive, and now you have blue, yellow, blue, that's negative. So that's the first step. Now I just told you that this is, nice to see that you can get this kind of hopping, but I just told you that a good description of the conduction electrons is given by the spin orbit coupled bands. So I'm just going to map this process that breaks inversion to the plus and minus, see the spin up and down, so this plus minus 3/2 that I said before. And if you do that mapping, you see that the inversion symmetry, so the fact that to the right and to the left, the hopping changes sign, it's still inherited, it's still present there. But now the most important thing, or the main extra ingredient that you obtain, is that the inversion symmetry happens in exactly the opposite way. So for a pseudospin up band will hop into another pseudospin up band to the right, say with plus, and the pseudospin down band will do it with a minus t. Okay. So what does this mean in terms of the Rashba-like language? It means that there is an effective field that is experienced by these soft bands that is just induced by this polar displacement. So, left movers and right movers are going to have a different energy. That means that you're going to have the characteristic shift of the pseudospin bands. And what we did was basically this whole description. You can do an expansion in U. So because, as I said, I'm looking at the linear coupling. So once you do this kind of expansion in U and expansion at small k, you get two terms for this process here, interorbital process. The second term here would be a conventional coupling to longitudinal modes, which vanishes at q equals 0 as it should. But the first one here, which is proportional to this polarization, if you want, so it couples to the polarization waves, and it's does not vanish at q equals 0. And now, once you do the transformation from the T to G orbitals to the spin orbit coupled bands, as you spin up and down, then you get this kind of 2x2 matrix where now the pseudo spin up will see exactly the opposite of the pseudo spin down band. And again, because I had this T to the right and to the left as a sign, then you get the fact that this coupling will be proportional to K, and so it breaks also inversion. And that's basically how you can get that non-magnetic polar displacement is coupling to the pseudo spin of the electrons. And what I showed here is a particular interorbital process. So with that, in our case, which had tetragonal symmetry set, the most general coupling. So if you have a cubic system or an isotropical cubic system, you should have this K cross sigma. If you lower your symmetry to tetragonal, you're going to have an EU. It's going to be split into an EU two-dimensional representation and a single dimension and one-dimensional representation A2U. And so this one here, this process is basically giving you one of the EU components, but in a very similar way, taking into account the other T2G orbitals that where these new hopping channels will be induced, you can get all the others. So I was using classical displacements until now. What as I said, my goal is to try to get an electron phonon Hamiltonian, so that then I can use it for superconductivity. So now that I have my classical displacements, I quantize them into a set of normal modes. So textbook way of doing it. You just make them, you decompose it into a set of orthonormal modes, and you write the previous expression into this formalism. And now what you get is an electron phonon coupling where the bare coupling will be proportional to K. It will couple to a particular polarization of the modes. And because I was showing you this particular process, there is this set here, which means that it will only couple this EU component of the coupling will only couple to the EU components of the polarization of your mode, which in this case it's going to be in X and in Y. So you can essentially get any lambda normal mode of your system, which can be longitudinal or transverse, and couple, if it breaks inversion in this way, it will have a finite coupling of this form. It will be proportional to this induced hopping matrix element, and of course also proportional to the 0-point motion of that particular mode. This would be the reduced mass and so on. So this is quite the standard form. Then the new part here is, first of all, that it's coupling. The vertex has this sigma set, so it's a little bit more like a spin kind of, like a magnetic kind of coupling. And then it has this K, so it breaks inversion, and that's because the mode that I'm coupling to is also, EU or A2U. It also breaks inversion, and then I can go ahead and assume write a basis where I couple only to the transverse component of the phonons. I get an analytical expression, and once I get the analytical expression, I can use this for calculating transport or superconductivity or whatever process you're interested in. And I just want to emphasize at this point that this pair coupling, as I said, does not vanish with Q equal. So at Q equals 0, it's still finite, but it's proportional to K. And that means that the lower carrier density you have, or the smaller the K of your electrons, then the smaller your coupling. So this is also not so conventional. And then I have my expression for the coupling, so I can do I can play the usual game. I convert into an effective electron-electron interaction, just like I do with a conventional electron phonon or with a convention or with a spin fluctuation mechanism. I have a vertex that is, as I said, now a little bit different because it has a sigma z. That's definitely different for a phonon, and then it is proportional to K. But I derive the interaction is going to have some momentum dependence, again because my vertex is momentum dependent. And then what we did was solve the Cooper pairing problem by looking at both even and odd parity solutions, which might not be very common to do for phonons, but in this case, because it's a particular phonon, you have this weird vertex. It was already pointed out here that you could have odd parity solutions. And indeed, that's, as I saw now, that's what we also found. So you solve the Cooper pairing problem. So that means that you get an eigenvalue for its different channel, and that gives you a hierarchy. And then you look at, your top 3, top 4, and see what kind of superconducting states are attractive and allowed by this Rashba-like coupling. And once you have that eigenvalue, the eigenvalue will be as usual. We are solving the weak coupling problem. So this is some density of states times some pairing interaction that will have the information of your phonon, so the bare coupling and the frequency. And then with that, you know that TC will be proportional to, the usual BCS kind of expression. And the highest lambda will be, in principle, this state that the system will condense into. So the leading channel for this mechanism is that we find is the S wave, or the A1 irreducible representation, and the maybe more unconventional or special characteristic of this pairing mechanism is that when you go to the second channel, which is attractive, we find it's an odd parity channel. Actually, the first 2 are odd parity, and in particular, the first competing channel would be the DC. So that's the one that has unequal spin pairing. So the subleading channel is P, and then we also find attraction in D wave. That's the one that is usually found in the case of cuprates from spin fluctuations, from antiferromagnetic spin fluctuations. So that's the other, I guess, one of the other take-home message, that you can first of all couple to this transverse optical ferroelectric mode, and if you map the Cooper problem, you get solutions that are attractive in odd parity and higher angular momentum even parity channels. So they are subleading, but they are there. And this sort of goes in line and in agreement with what other groups have found in similar kind of studies. And so I showed how you can couple to this mode. I showed what kind of superconductivity you can expect. And now let's do some estimation. So is this a pairing mechanism that is relevant for this system, for strontium titanate? So in order to do that, what we did is get sort of in tandem work with this microscopic model and the Ab-initio frozen phonon calculations, and all those were done by Eleonora and Paolo, which are also in Rome, based in Rome. So in order to do that, the first thing that we had to do is you have to freeze a phonon, and then you freeze the phonon, and then you recalculate your electronic band structure in the presence of this phonon. And then from that reconstruction, you obtain the coupling. Now, the first thing to notice is that the first thing you need to do is like, okay, what kind of phonon is the one that I should freeze? And in this particular case, you can have either EU or A2U phonons, and any polar distortion that you have should be a combination of a complete basis. So what we did was get, first of all, find a basis that is complete in this case, and then compute the coupling to all of these modes. And the idea is that because it's not completely clear the actual, if you want, eigenmode that is relevant for STO. So as I said, it is known, or we know from neutron scattering and hyper-Raman experiments that most of the contribution comes from this S mode here, where you move the titanium and the oxygen cage against each other, out of phase. But then in principle, any mode will have a finite contribution. This mode will also have a finite contribution from this phase. So what we did was find a way of mapping the entire phase space in terms of the coupling, and then once you get different possibilities for the particular eigenvector for the mode, you can get an estimation. But now, for simplicity, what I'm going to assume is that this mode is completely well described by this S1, this latter mode. But I just wanted to mention that in principle, it's you can get the full picture and make the mode to be a little bit more complicated. So you have some freezing of the mode. So basically, in Ab-initio, what they do is they move the titanium a little bit to the right and the oxygen case a little bit to the left, and recalculate the electronic band structure. And from the model that I just showed you, we know that it should couple to linear order in U with this Rashba-like form. So you'll have some induced hopping. Now you are in a tetragonal system, so in principle you'll have 2 EU components and 1 A2U one-dimensional component. And then what happens to these modes, what one expects, as I said, you should also expect them to shift whenever you are along a direction that is perpendicular to this polar displacement, because when it's parallel to the polar displacement, there is no pseudo-spin split. And we do know from this model what the form of this pseudo-spin split should be like. So it's going to be, first of all, linear in K. This is, Rashba-like. And then depending on the direction of momenta, you will have the different components of the coupling shifting the two pseudo-spin up and down bands. So essentially, looking at different momenta direction, you can extract these T primes, and then you just plug them in here. You have the reduced mass and the frequency of the mode from experiment, which is, I'm always doing, taking the coupling from the, I'm solving the coupling problem for superconductivity in the paraelectric phase. So I'll take those values from there. I know what the T prime is, and then I know what the electronic filling or Fermi energies are. So then I know also what the relevant momenta is. So that's what we did. This is some examples of how Ab-initio looks like. So I'm already plotting here the difference between up and down along different momentum direction, and normalized by respect to this U. So we do this for different U values, and we make sure that when you plot this, this quantity is not changing, so that you are in the linear regime. Because of course you can also get higher order terms. So numerically, you can go to U squared, U3, and so on. So you have to make sure that what you're extracting is the linear form. So that's how we do it. So this is the examples you get for bands 1, 2, and 3 for a particular mode, which is in this case in plane. And you see this split, which is linear in K, as we were expecting. And then how basically the slope of this is determined by this T prime along different directions, and extracting or fitting and those slopes from that you get from Ab-initio, then we get the G's. And the second take-home message would be that the estimates we get for this Slater mode here for the lowest band, for example, of course, so essentially once you do Ab-initio, you get the coupling through all bands and almost so on. You just want to, get 3 of the estimates to get a feeling of what kind of numbers we're getting, and they are quite significant. They are pretty remarkable. So there was some estimations a few years ago saying, okay, let me assume that it is proportional to this inter-site hopping matrix element, and then I'm going to be overestimating this coupling, and though that would be something like the thing that they were getting was 3 times smaller than this. And so the first take-home message is that, at least from Ab-initio calculation, seems like the linear coupling between these electronic bands and the transverse optical phonon polar mode is significant. And now, once I have this, I already worked out the superconducting problem, and I do have the lambda BCS in terms of this G, and then I can get an estimate. So let's now see how that one looks like. So first of all, let me make a few points, comment a few points about superconductivity. So here I'm showing experimental data, TC versus carrier density, and now this TC, so the different colors is because there is different ways of doping the system, and there is, a big question mark is why is it that with some kind of doping you don't get TC, you don't get superconductivity in this extremely dilute regime. That's one of the questions, but something that I also think is a little bit particularly interesting is the fact that there is not been reports of diamagnetic character below this, I don't know, critical densities already below the, so for the, essentially for the first one, so below 10 to, I don't know, I think the record is a paper in the 60s or the 70s, in 7, 10 to 18. So when you are in this optimal doping, so it still is quite dilute, it's small fermions and all that, but I'm showing here the typical measurements that one gets which signal the transition into superconducting phase. So you have the specific heat jump here, you get the magnetization here, and resistivity drop to 0 happens at slightly higher temperatures. That's a common feature in all this area, but nevertheless, you do get bulk signatures. What happens in this lower regime instead is that there is no bulk reports of superconductivity, but they do get, very sharp resistivity drops. So another thing that I would like to emphasize is that at least in this regime, there has been both tunneling and optical spectroscopy of the superconducting order parameter, and when they do 2 delta divided by TC, they get 3.5. So it's basically a better BCS material than aluminum. It's really the prototype with coupling BCS from these measurements here. So now that I've set a little bit of the experimental background, something that I think is pretty remarkable in this material is the fact that if you have a TC of around 0.1, 0.4 Kelvin, we know it's weak coupling, and then you extract from TC proportional to the exponent of -1 over lambda. What kind of lambda should you get? That is of the order of, let's say, 0.2, which is within weak coupling. And then this lambda, as I said, it's going to be proportional to the Fermi, to the density of states times some effective pair interaction that can be from, this transverse optical phonon. It can be from any other mechanism. But at least within weak coupling, that lambda should be of this form. And then you put the numbers into the density of states, because it's an extremely dilute system. The density of the states are very, very low, in particular in this low density regime. So you say you put the density of states is around 0.04. These, by the way, have been measured by specific heat. So it's quite well known what these numbers are. And you put in the numbers and the kind of pairing interaction that one would get from any weak coupling mechanism, no matter from, whether it's coming from one phonon, another, or anything else, should be of the order of 5, 6, even here could be 10 EVs. That's an extremely large interaction, in particular if it's going to come from electron phonon. So this is just something that I wanted to point out. Nevertheless, as I said, these are resistive transitions. So as soon as you go to this other regime here, where the density of states grows by about an order of magnitude, then this goes down to 500 MeV, which is a little bit more into the conventional limits for non spin or coulombic interactions. So now that I've said this, I go back to our model. We get the expression for G. We get the estimate from Ab-initio in this induced hopping. We place here the experimentally measured frequency of the mode. And then I have that my lambda BCS is the density of states times U squared divided by the frequency. So I get two numbers in two different regimes. One is for this very low density of states, which gives me an extremely small lambda BCS. So in principle, this mechanism in this low density of states cannot support superconductivity on its own, not with this number. Remember that it has to be of the order of 0.1, 0.2, 0.3. Instead, when I go to this higher density regime, so where my electrons and the electronic KF increases, then say that increases by a factor of 3. So G is proportional to K, lambda is proportional to G squared, so I get a factor like a power of 2 there, and then the density of states in a 3-dimensional material is also proportional to K, so this lambda goes with K to the 3, and then once I get KF to be 3 times larger, 3 to the power of 3 is 27 times larger lambda, and then I do get a lambda in this regime that could in principle be a good candidate for superconductivity. Now, a few words about what is then going on in here. Something that we have speculated or proposed that could be going on is a scenario of inhomogeneous superconductivity. So because you have proliferation of tetragonal domains in this system, you in principle could have a situation where in some of the regions of the sample, the mode gets even softer. So it was already a soft mode, but it gets even softer. So say it gets a factor of 3 to 5. Then because lambda is proportional to G squared divided by omega, and G squared has another frequency, so that means that lambda is proportional to 1 over omega squared. Then if this frequency here gets locally softer, that would mean that you would have locally some regions where lambda is of the right order of magnitude, and that would mean that you would have sort of like a distribution of TCs. And then you could have at some point those paddles would be connected, and you would have a superconducting path for resistivity drop. Nevertheless, that would not give you a diamagnetic, you wouldn't have phase coherence. It would not give you a diamagnetic signal. So it's more a filamentary superconductivity kind of picture. But you know, there is some experimental indications that this could be what's going on here. But I mean, who knows? This is just a possibility. But anyways, I just want to emphasize that this mechanism then is fine if you assume that, you know, this lowest band has the most contribution. Then you just estimate what the contribution would be, and then you get a lambda that is more or less of the right order of magnitude. And then I don't know how I'm doing on time, but I'm basically almost done. So I have this one last slide. I wanted to point out very recent experiments. I mentioned them in the beginning. So I'm going to go away from STO and go to this sibling. It is also an incipient ferroelectric, but as far as I know, there has been no reports of superconductivity once they dope it, and I think they have looked for it. But in the last few years, there's been this community of heterostructures reporting that they do find a very large TC, and large in this system. They are so dilute that, you know, having a 2 Kelvin superconductor for such a dilute system with very small density of states and so on, as I said, is pretty remarkable. And what they are saying, and now it's been confirmed by, I think, 2 or 3 different groups, that, you know, you get KTO, you grow it on different types of substrates, or you dope it in different ways, and you get this quite robust TC. As far as I know, there has been no bound yet on, you know, they can dope it more for technical reasons, but this TC keeps growing linearly. And there also seems to be, you know, the important fix seems to be on this KTO part of the sample, because you change the substrate and you basically get the same results. And in a very recent paper, there was something that was, I think, something that is extremely important that could shed light into the mechanism, because what they found is that if you grow this KTO along different with different crystallographic orientations, you have the two-dimensional electron gas with a different crystallographic orientation. The TC changes a lot. It has this extreme sensitivity. So here I'm showing the results. So you have TC along 1 with the growth along the KTO along 111, which is about, I don't know, 2. It gets to 2 Kelvin. Along 110, it has dropped significantly by a factor of 2. It gets to about 1 Kelvin, and if you grow it along 001, then down to the lowest temperatures, they could not find any superconductivity in this experiment. And what they claim is that if you consider a model where you're coupling the electrons linearly to this transverse optical mode, you can explain, at least qualitatively, this kind of extreme sensitivity to TC. So that puts this linear coupling to the transverse optical mode as a very relevant mechanism. But what we are doing now is essentially using the same kind of approach that I have described to try to estimate this Rashba-like coupling. It is a linear coupling to the transverse optical mode, but now in this system instead. So with this, I got to the conclusion slide. So let's see. I have described the model that we have developed to show how you can get coupling between electrons once you take into account spin orbit coupling to a mode that breaks inversion, which in this case was a soft transverse optical mode. So this is relevant for any system where you have a ferroelectric phase, because in principle or often you'll have that soft transverse optical mode. I showed how this coupling, it looks a little bit like Rashba, so you get the coupling to the spin of the electrons, and it is also odd in momentum, so it has many of the Rashba-like characteristics. It's not exactly Rashba, but it has the same form. Then starting by weak coupling superconducting pairing problem, we found that the leading instability is this way for A1G if you want, but interestingly, you also get attractive channels in the higher angular momentum cases. So the first one was one with odd-parity, which was a P wave, and then you also have attraction in the D wave channel. And then I showed some estimates of this model for STO, which is a prototype incipient ferroelectric, and a lot has been done in terms of superconductivity. And first of all, we found that the Rashba coupling to this soft ferroelectric mode is substantial, and then to the corresponding coupling pairing coupling constant can explain TC when you are in the optimal doping, so in this multiband regime where bulk superconductivity has been reported. But if you are in the low doping one-band regime, it may explain it if you take into account the fact that you have these domains and there may be this local softening of the mode, and then you would have a local lambda that is much larger, a distribution of TC, and then this kind of filamentary superconductivity picture. And this seems to be to some extent consistent with some of the experimental reports in this very dilute regime. And then as an outlook, I would like to point out mostly three things. First of all, whether, how relevant is this pairing mechanism for other materials. So I would say that the most relevant right now would be these heterostructures with KTO. This is the case I just discussed. And then I think it's also very interesting the regime where you take the system into the polar phase. So all that I have described was done in the paraelectric. So the system was inversion symmetric. So now what happens in the polar phase? Now in principle, you can't say even channel and odd channel for superconductivity. The say A1G irrep in that case would be in general a mixture between these even and odd, or like singlet and triplet, and then very little has been done experimentally, even less theoretically. And I mentioned that there is this recent work claiming that topological superconductivity, that it might be a very relevant platform for topological superconductivity. And then finally, I would also like to highlight, I said in the beginning that there is another way to couple to this mode, which is going to the next order in coupling. So I stayed at linear order, that some people have gone to the second order, to this mode. And these also, there is quite strong indications from numerics that the coupling to second order is very large, which is not usually the case, but again, these polar materials might be not so usual in this way. So something that we are also working on is basically generalizing now, trying to estimate the contribution that you would get to pairing instead of from this single coupling to linear order, which is the usual one. You have this electron coupling to one phonon and then compute this diagram. Now instead going to second order where you get, say, the electron to emit or absorb two phonons, and then you would have this kind of diagram instead. And with that, I thank you for your attention, and I'll be taking questions.
Right. Thank you, Maria, for a very nice talk. Now the session is open for questions. I know that Noah had one. So Noah, you want to go first?
Hi, Maria. Hi, Adrian. So the question is about trying to understand this Rashba coupling. and how it may apply to other materials, or even, I mean, how it applies to this material. So I'm thinking about the cuprates, that's where we come from. And I'm wondering if there's a similar kind of mode that might be interesting to look at in the cuprate case, and how would we know it?
So cuprate. So I would say, like, the answer is I haven't thought about how this would apply to cuprates. But if I had to look at something, I would look at a mode that breaks inversion. So in cuprates, you would have to look at some some mode that has the U, T1U or A2U, or and that's all I can say. I don't know. I mean, so the motivation certainly for this is that you have a mode that is very soft, that is close to an ordered phase, which is ferroelectric. In cuprates, that is, I mean, it's a very complete phase diagram, but as far as I know, there is no ferroelectric phase reported so far. So I would look at the coupling to a mode that breaks inversion. Now, I'm not sure I would expect it to be particularly important, especially if it's not very soft. So this coupling, at least at the exchange level that I discussed, will be proportional to 1/omega squared. So if the frequency of the mode grows, then the coupling is quadratically reduced because it's 1/omega squared. And then, once it gets harder and harder, the coupling very quickly dies. So you would need to find a mode that breaks inversion and that is sufficiently soft to have a significant coupling. But as I said, I haven't thought about so I always had in mind systems that are close to a ferroelectric or polar phase, because then in that case, you are very likely to find a mode that has very low frequency. So it's soft.
All right, thank you. Frank Marsilio has a question. Please, Frank, unmute yourself and feel free to ask.
Hi, okay, so there are kind of two related questions, I guess, which is, especially if you're considering the quadratic coupling, but even before that, because of the mode softening, my expectation is that there'll be important roles possibly due to anharmonicity and even due to the width of the phonons themselves broadening. Are you accounting for that somehow in this?
So I'm not including anharmonicity in the sense that what we do is we freeze the phonon, and then what we take as the 0-point motion, which would be given by the reduced mass and the frequency of the mode, we basically assume that all of those anharmonic processes have already, renormalized my bare frequency of the mode, and I'm taking the frequency of the mode from the experiment. So in that sense, I'm not directly taking into account, I'm just taking the value from the experiment. But probably the anharmonic processes will be important in this, just looking at I guess you're thinking, just looking from the lattice point of view, right? How this mode talks to all the other modes and so on. So I'm basically assuming.
And to the electrons.
And to the electrons. So onto the electrons, I haven't. As I said, I'm only taking the linear coupling, and that's where I stop. But there is substantial quadratic coupling, and there is probably substantial, higher order coupling, so cubic coupling and so on. But that I haven't looked at.
I'm thinking even of in the linear coupling problem, there's a difference of electrons interacting with well-defined phonon modes versus electrons interacting with phonon modes that are not great quasi-particles because they have a width and because there's anharmonicity.
Right. So the answer is I've solved the problem doing the first thing. So I'm assuming that this is a well-defined mode. Yes. Yeah. So it has a propagator which has infinite lifetime and all of that. Yes. Yeah. Yes. So it's a d squared d where d of the propagator is a conventional phonon with an infinite lifetime. Yes, I haven't looked at anharmonic effects for this coupling, but I'm expecting, I guess I would expect strong temperature effects for sure. Are you more thinking that maybe the bare coupling would be strongly renormalized? Is that where you're getting at?
No, I'm not. I'm just inquiring because
okay.
You know, it's relevant for all of us, but I'm not aware of significant work in that direction. So that's why.
Right. No, me neither. Actually, me neither. I know that. So, for example, when in the Ab-initio community, I know that they tried to describe this mode, and the first problem that they got is that the code was telling them, okay, use the functional you want. The system is ferroelectric, and they knew, okay, but the system is not ferroelectric. It should be paraelectric. And then what they found is that they had to take these anharmonic effects, at least at high temperatures. That's all they did, as far as I know, they went down to 200K, so they never really went to study the softening of the mode. Then once they took these anharmonic effects into account, this so-called SHA kind of method, I don't know if, then they recovered the fact that the imaginary part of the mode was not negative but positive, and then they recovered the paraelectric behavior. And this is, again, because probably this system is well into it's a quantum paraelectric, and there is strong fluctuations, quantum fluctuations and so on. Yes, but that I have, as I said, I have started from the more basic first step, which is take a well-defined mode, which would be my phonon, and then take the frequency that has been renormalized already, and take the experimental, low temperature frequency, which is 1 MeV or something like that.
Okay, thank you.
Right, Steve has a question. Please, Steve Helberg, feel free to unmute yourself and ask directly.
So I know you were focusing more on the low doping regime, but can you speculate about why TC, as you go to higher dopings, then drops back down to lower temperatures?
Yes, I can. Actually, I have a backup slide for that. So I said the lambda. Okay, so all I can say is about, I'm going to comment on this mechanism, which, as I said, is linear coupling. So it goes with Kf to the 3. And then, lambda, you keep growing, you keep doping the system, Kf keeps growing, why isn't lambda growing? And the answer is that even at the linear coupling of U, when you take into account, this is something that we'll put on archive soon. So even when, let's see if I have it here. Oh yes, here it is. So even when you take you say, okay, I'm going to couple it linearly, and I'm going to fit to this linear in K coupling. So from Ab-initio, you can already see that this linear in K gets up to 1 point, and then it actually stops being linear in K, and rather than increasing it, it slows down. So here I'm showing the G that you would expect as a function of Kf. Okay, so the full lines are from Ab-initio. So you in the beginning it grows linearly, right, as it should. This is Rashba-like. This is for the 3 different colors of all 3 bands. And then at some point it deviates from this Rashba, and it doesn't keep growing up to infinity, but it sort of saturates and drops. And then you calculate the effective interaction that you would get naively from this kind of rigid shift point. You get something that goes up and then goes up. This would be the contribution from this mechanism. Now, in the real system, why the dome happens, I don't know. But from this point of view, you would definitely get that. Another thing that one has to take into account is the fact that because the electrons couple quadratically to this phonon, the phonon gets harder. A little bit, not so much. Maybe it goes from 1 MeV up to 3, 4 MeVs, and any mechanism also that is proportional to 1 over omega will also drop pretty fast. So there's these 2 effects. One, the linear coupling is Rashba-like, but it stops growing, saturates, and then dies. And then at the same time, you also get a softening of the mode. And that would naturally give you some kind of dome in this very, basic rigid sieve point of view. Of course, should also, I would say that one should also look into how the screening from the electrons when you start to dope it and you have 10 to 23 electrons, screening that interaction, how that evolves with doping. That would be a third thing to consider. But already the first two give you an idea, a very simple idea of why this interaction would stop and peak and die.
Great, thank you.
All right, any other questions? All right, if we don't have any more questions, let's thank Maria one more time. Thank you, Maria, for joining us today. Thank you, everyone, for attending. And see you
Thank
next
you for your attention.